We are very much privileged that this evening we are going to have a special lecture from one of the greatest plasma astrophysicists of our time, Professor Kazunari Shibata of Kyoto University. So he does not need any introduction to the participants of Asia-Pacific Solar Physics meeting, but since there are several other persons also in the audience, and for the sake of completeness, I shall say a few words about Professor Shibata. So he was born in 1954, and apparently in his childhood, he wanted to be a scholar living alone in the mountains. But luckily for us, I think this Mr. Tompkins series of books of George Gamow, which many of you might have read, these fantastic books, I think finally convinced him that he wants to be a physicist. And then he studied in Kyoto University and obtaining a PhD degree from there in 1983. Then he was, for several years, he worked in places like Aichi University and National Astronomical Observatory of Japan, eventually returning to his alma mater, Kyoto University, as professor in 1999. And for several years, he also has been the director of Kwasan and Hida observatories. And in this age of specialization, he is somebody who has worked virtually in all different areas of plasma astrophysics, starting from the sun to the plasma outflows in star-forming regions to active galactic nuclei. But of course, we solar physicists would like to consider him as one of us because of his fundamental contributions to his models of reconnection, solar flares, and solar jets driven by reconnections. So he also has produced a very large number of distinguished students and postdocs. And since this is a meeting in this talk in the Asia-Pacific meeting, so I may mention that some of his former students and postdocs had got very important honors in these meetings. For example, from the last APSPM, we have been giving an Young Career Award. And in the last APSPM, the first recipient of the Young Career Award was Peng Fei Chen, who was mentored by Shibata-san. He was Shibata-san's postdoc. And in this APSPM, the runner-up for this award was Masumi Shimojo. So he was again, I think, Shibata-san's PhD student. So in that way, I think he has his students have been very important, I think, star participants in these conferences. And as Shimojo-san mentioned that he was first received the training as an undergraduate student from Shibata-san, and that the paper he wrote as an undergraduate student, that has remained his most highly cited paper. So I may mention that I also had a personal experience of how he can inspire undergraduate students, because a few years ago I was a co-author with him in a paper on the question of whether super flares can occur on our sun, and he involved several undergraduate students to do this, to do the very interesting data analysis for super flares. And couple of papers which came out of that work, they are so highly cited that I guess for many of those undergraduate students, probably these papers will remain the most highly cited papers of their life. And he has been the author of a very well-known book, Plasma Astrophysics, by Tajima and Shibata. And also I may mention that he is an author of a popular science book on the sun in Japanese. So unfortunately, I do not know Japanese, but I have heard from many people very high praise for that book. And in fact, a few months ago, when my own book, Astrophysics for Physicists, was translated into Japanese, I really regretted that I don't know Japanese. And naturally, he has won many important awards and honors. For example, from Astronomical Society of Japan conferred this Hayashi Prize on him, and also for his popular science book, he received Kodansha Science Prize. I don't know whether I pronounce it correctly. And then, most importantly, only a few months ago, he became the sixth recipient of Chandrasekhar Prize, one of the world's most prestigious prizes in plasma physics, awarded by Asia Pacific Physical Science Society. And I may mention that I had the privilege of nominating Shibata-san for this award, and when when this news for his winning this award came, so I was almost so happy that as if I myself have won this award. So with these awards, I shall invite Shibata-san to come and deliver his talk, and before he starts, we shall felicitate him in a traditional Indian way.
Yeah. A bit difficult. Thank you very much.
Yeah, you can.
Yeah, Chowdhury-san.
You want to keep this, or you want to? It's up to you. You want to have that
Please,
now?
please.
Should I pack it up?
Yes,
Or you want
that's a
to-
good idea. Yes. Yeah, Chowdhury-san. Yeah, thank you for your excellent introduction. I don't have to say anything now. And first slide is actually introduction of Chandrasekhar Prize. And the last summer, I heard amazing news from Association of Asia Pacific Physical Societies, Division of Plasma Physics. And my reason is pioneering and seminal contribution in solar and astrophysical magnet hydrodynamics. And here I show you, this is the proof that I received Chandrasekhar Prize. And also, please look at the name, Don Melrose, our colleague in Asia's Pacific solar physics member. And here is also medal, Chandrasekhar's face. And I'm really happy to give a talk here because this is a Chandrasekhar auditorium. So best place to give a Chandrasekhar talk, prize talk in the world. And so I'd like to start my talk by introducing Chandrasekhar. Of course, you are Chandrasekhar, you know very well. Chandrasekhar has been a superhero for me since my undergraduate student time in 1970s. Through the textbook on hydrodynamic and hydromagnetic stability, published in 1961, probably many of you know. And but also I was very struck by the Chandrasekhar's tragedy that his theory on white dwarf was not accepted by Eddington. So from a very early time undergraduate student, I want to be a researcher like Chandrasekhar. And in 1992, Chandrasekhar's biography was published in Shonen Jump, Japanese manga magazine. and I bought this magazine. Only time I bought manga magazine by my money. This one. And this is a really impressive, good manga story. When Chandra is going to UK from India, he discovered Chandrasekhar theory, original theory. And then after reaching UK, he talked to Eddington. And Eddington immediately understood that the Chandrasekhar theory lead to a generation of black hole. Very surprised. And as you know, in a UK Astronomical Society meeting, just after Chandra's talk, Eddington rejected because Eddington didn't like black hole. And of course, Chandra was very shocked. But because of this, no astronomer in UK they believe Chandra's theory. Therefore, after marriage, Chandra had to go to United States. Also, he had to change his field from stellar structure work to plasma physics, and so on. Therefore, I received the Chandrasekhar Prize. And 50 years later, finally, his white dwarf theory was accepted, approved, and he received a Nobel Prize. So this manga story is much more useful than usual textbook. And this is evidence of that Japanese manga level is very high. Okay, so if you come to my room, office in Japan, I'll show you everything, this manga. Okay, so from now I will talk about these subjects. This is actually my research history in 40 years or more. So let's start from astrophysical jets. When I was an undergraduate student at Kyoto University, this is a picture when I was 22 years old. Lot of hair, long. My dream was to resolve the puzzle of active galaxy nuclei and their jet, because this was the biggest puzzle in astrophysics. These are very famous astrophysical jets, active galaxy nuclei. This is Cygnus A, radio galaxy. Here is the active galaxy nuclei and jet. And this is also famous quasar, 3C273, like a star, but has a jet. And later, galactic disk was discovered around this AGN. And from 1960s to 70s, it was found that these quasars are located at cosmological distance. That means released energy is very big. In those days, AGN is the biggest explosion in the universe after Big Bang. And finally, AGN were found to be a nucleus of young galaxies. And this is the first astrophysical jet observed in history of astronomy in 1918 by Curtis, M87. This is the big elliptical galaxies and jets, nucleus. And radio astronomy, astronomical observation revealed this visible, light optical jet is very bright in radio. And also, this jet collide with the intergalactic plasma to form shocks and become very bright radio lobe. And I learned AGNs are very far from the Earth, more than a few billion light years. So it seems difficult to observe AGNs directly. But I want to resolve the puzzle of AGN jets. So I thought I should take theoretical approach based on MHD plasma theory, and solar physics. Since the sun shows many jets similar to AGN jets, even in those days already surges, H-alpha jets are already well known. And I think this approach was very successful. Because this is, again, M87 Galaxies, and new observation revealed the region near nucleus. And finally, black hole shadow was observed in the last year. But still, jets are not seen. Okay, still we need more time. Therefore, observational development of observational astronomy was not in time until my retirement. Okay. And after 1981, protostellar jets are discovered, similar to AGN jets in young star. These are observed in visible light. And this is a jet with a speed of 100 kilometers per second or so. And the length is 1 light year or so. But here is also shockwave, very bright hot spot, also here. And this is the AGN jet observed in radio wavelength, much larger, 3 times 10 to the 5 light year, and speed of jet is 0.99 c light speed. But both are very similar. So I thought approach using MHD is a very important. That is scale-free. So self-similarity of hydrodynamics, MHD, is found. And what is the origin of astrophysical jets? This is a very simple summary of 3 different kinds of astrophysical jets. One is a jet from AGN, active galactic nuclei, and second is a closed binary system, jet from closed binary system. And third is the young stellar object. And the central object is different, very different. And jet length also very different. Jet velocity is also very different. But interestingly, jet velocity is comparable to the escape velocity of a central object. So this is a very universal property. Very important hint to understand jets. And from this simple table, you can immediately understand relativity is not essential. Formation of jets is also possible in non-relativistic normal star. But this is the important point. And then it is found that plasma accretion occurs onto the central object in these objects. And accretion disk is formed because of angular momentum conservation. And it is clear the energy source is the gravitational energy. And accretion disk play a key role. Now this is a simple one we can understand. The problem, how to convert gravitational energy to kinetic energy of jet. And especially in the black hole, there is no surface, rigid surface. And what is acceleration and the collimation mechanism of jet? But this is a very important question, still fundamental question in astrophysics. And more than 30 years ago, I thought there are a lot of hints from the sun. And that is the magnetic field. Magnetic field may play an important role. Then I started to study solar jet. And at Hida Observatory of Kyoto University, I collaborated with Kurokawa-san in 1980s and discovered this H-alpha jet-like prominence eruption. Before flare eruption, here is a helically twisted filament, and this suddenly erupted, then showing spinning motion. This is a Doppler shifted image, blue shifted image, red shifted image, and the composite. So this jet rotate like this. So the direction of the rotation is exactly the same as the unwinding direction of this helical jet. So we can immediately develop MHD model of a magnetic twist jet with Uchida-san. And we thought this magnetic twist jet can be applied to AGN, astrophysical jets. And in the case of the sun, how is a helical magnetic twist generated? And we thought magnetic field can be easily twisted inside the convection zone because of high energy density. And if a twisted flux tube emerge above a solar photosphere, then plasma beta becomes lower than 1, and magnetic force becomes dominant. And then if reconnection occurs between the twisted tube and open field, then such a magnetic twist can be released to open tube, becoming jets accelerated by magnetic force with helical motion, spinning motion, and eventually become alpha waves. And in the case of accretion disk, in this case, much easier. Accretion disk itself is a spinning motion. So a vertical magnetic field can be easily twisted. And so magnetic twist jet can be easily created. So after getting PhD in solar research, I started to develop a MHD model of astrophysical jets with late Uchida-san. Actually, I'm a first person who developed a two-dimensional MHD simulation of astrophysical jet from accretion disk in the world. The model is very simple. We assume gravitational objects here and rotating disk, accretion disk, and assume uniform vertical magnetic field to the disk. Then start. And disk start to twist magnetic field, and then torsional alpha wave propagate. And during this process, angular momentum is extracted. And accretion disk gas can fall onto the central object further and further. And the magnetic field is more and more twisted. And the magnetic pressure become very large. And finally, plasma start to be ejected from accretion disk. But this is our simulation result. And time scale is, in this case, less than 1 rotation of disk. And acceleration force is both magnetic pressure in this highly twisted magnetic field, and also magnetic centrifugal force. Strong magnetic field is rotating, then there occurs centrifugal force along field line. And finally, we found jet velocity is comparable to the rotational velocity of the disk. And near the central object, this is also comparable to the escape velocity of a central object. So this can be a unified model of astrophysical jet. You remember the jet of the velocity is comparable to the escape velocity of a central object. And the escape velocity of the black hole is the light speed. Therefore, a jet ejected from near the black hole has a velocity very close to light speed. but this is a Newtonian MHD simulation result. And 10 years later, but still computer is slow in those days. Collaborating with Dr. Ryoji Matsumoto, he is also from Kyoto University, younger than me. For the first time, succeeded to develop a 3-dimensional MHD simulation of jets. And this is the magnetic field lines. And magnetic field become highly twisted, but nevertheless, in a non-linearly stable. By the way, such a twisted structure become unstable for kink instability, as well known from solar prominence eruption. But in this case, because of a high-speed jet, non-linearly stable. And finally, we succeeded to develop general relativistic MHD simulations with the help of Koide-san and Kudo-san. This is the first in the world. And but the physics is the same as the Newtonian MHD. But the velocity of jet still not so high, only a fraction of light speed. But actual light, jet velocity is 0.99 or more. So we need to solve this problem. Still, this is not yet solved in the world. Then I'm going to discuss solar flare jets. And as you know, I and Magara-san wrote this review nearly 10 years ago. And before discussing solar physics and reconnection, I'd like to show you some entertainment. Recently, I have been collaborating with the musician Kitaro-san. He is a famous Grammy Award winner. And he visited Kazan Observatory 6-7 years ago. Yeah, more. Anyway, please enjoy. This music expresses disaster in ancient days. How solar flares can be a cause of a disaster in our civilization. This is an X-class flare observed at Kyoto in HR. This is a very famous active region just before X-class flare observed by Shibata. Now energy is accumulating. during solar minimum. Very maximum. Very bright. So full of solar flare. And the flares, energetic particles. This is again very famous prominence eruption. I like this movie very much because a lot of Lady Taylor instability occur. And also the same prominence eruption and the flares observed by SDO in the different wavelengths, EUV. And the same movie again, finally, please notice EUV waves, shock waves from flares. This is the largest prominence eruption in the history, observed nearly 70 years ago. In the United States. And this is a very new prominence eruption observed by Hinode. This is a X-class flare observed at Hida Observatory in H alpha. And this is the same flare observed by SDO, AIA. You can see beautiful prominence eruption, filament eruption, and the flare in EUV, and this is the same flare in H alpha. We have not yet published this data. And this is a coronal mass ejection from this prominence eruption. This is a famous stereo movie for different agents. We can see interplanetary blast wave. This is again Yoko soft X-ray movie. Okay, did you enjoy? Thank you very much. If you want to see this movie again, please buy this on Amazon. Okay, then I'd like to discuss the physics of solar flares. What is the mechanism? This is a well-known standard model, originally developed by Carmichael, Starrock, Hirayama, and Kopp Newman. Now I don't have to explain this. And Yoko satellite phenomenologically established the reconnection model of flare because this is the H-alpha image of a typical two-ribbon flare at HIDA. This is a simultaneous soft X-ray image of the same flare observed by Yoko. And we can see that loop, and especially cusp-shaped loop, is just above a two-ribbon flare. And this is what we expected for solar flares based on the reconnection model for many years. And so at this point, many solar physicists agreed solar flares mechanism is a magnetic reconnection. But of course, the magnetic reconnection physics itself has not yet been established, even in plasma physics, as a plasma physics. So still, we need to study, continue to study. And Yoko soft X-ray observations revealed that plasmoid ejections are ubiquitous, from very small impulsive flare, compact flares, to long duration, large flares, and even to the coronal mass ejection related to giant arcade, which previously not considered to be a flare, but now I can say physically same as the solar flares and caused by reconnection. And these various flare-like phenomena are all explained by this unified model. That is the point I have proposed for many years after Yoko launch. And I emphasize the importance of plasmoid to induce fast reconnection. And also, Yoko discovered a lot of jets, X-ray jets in the solar corona, and as Shimojo-san already discussed. And there is also evidence of reconnection in morphology, not only morphology, but also some energetics physics. And our colleague, Yokoyama-san, succeeded to develop a very nice MHD simulation model of jets using reconnection mechanism. And 10 years later, new satellite Hinode discovered ubiquitous chromospheric anemone jet near sunspot, active region. And this is much smaller than coronal X-ray jet, but morphology is quite similar to that of a coronal X-ray jet. And again, we found evidence of reconnection like this, and succeeded to develop a MHD model of reconnection jet model. And this is a summary of observations, various flares and jets in the solar atmosphere, from micro flares, impulse flares, long duration flares, and giant arcade just below the coronal mass ejections. And please look at these numbers. These numbers, size, lifetime, very different. But if we normalize time scale by alpha n time, then this non-dimensional time become all comparable. So this is evidence that these apparently very different flares and flare-like phenomena may be unified by a single physical mechanism. By the way, the inverse of this time scale is a non-dimensional reconnection rate. So normalization by alpha n time is very important. But there is still remaining puzzles. In small scale flares, we usually observe jet or map, classical surges. But for larger flares, we observe plasmoid, spray or prominence eruption, and larger scale coronal mass ejection. So how can we explain these differences? So I start to propose this unified model, plasmoid-induced reconnection model. In the case of a very large flares, this plasmoid or flux slope in 3D can be remained in outer corona or even in interplanetary space because magnetic field is weak. But in the case of small-scale flares, ejected plasmoid or helical flux tubes or filament collide with the ambient field and then lead to a secondary reconnection and finally lose original shape, helical filament shape, to become a jet or helical jet. And finally, alpha waves remain. So this is a hypothesis I start to propose. But as you have heard Shimojo-san's talk, Hinode beautifully proved this hypothesis, found evidence of this kind of a physical process. But as I mentioned, Romua-san and Sarnu-san start to call this, 何やったっけ、なんとかモデルって言ってI forgot the terminology. But they argue their idea is different from my idea, but from physics point of view, basically similar. Please study this point physically, but that is a message to young researchers. And one more important message to young researchers is that still magnetic reconnection has not yet been solved. Most important question, what determines the reconnection rate? And magnetospheric observations and collisionless plasma theory suggest first reconnection occurs if the current sheet thickness becomes comparable with the ion Lamour radius or ion inertial length, which is of the order of 1 meter or less in the solar corona. But this microscopic scale is much smaller than the flare scale. So how can we reach such small scale to lead to anomalous resistivity or collisionless reconnection in solar flares? In the case of a magnetosphere or a laboratory, their scale is close to such a microscopic scale, so easy to explain. But our problem is much more difficult than magnetospheric reconnection or laboratory reconnection. This is the important point. So I started to propose plasmoid-induced reconnection and fractal reconnection with Tanuma-san, one of my graduate students 20 years ago. But actually, basic idea is partly from Tajima-san in Texas. In 1986 to 1987, I was staying University of Texas at Austin and collaborating with Tajima-san on plasma astrophysics. And we started to write a textbook on plasma astrophysics and completed and published in 10 years later, like this. And the original price is $70, but 5 years later, become cheaper. And we met 2010, became a bit old. But by the way, in the last year, Tajima-san received the Chandrasekhar Prize. So yeah, but in his case, he is also a candidate of Nobel Prize. Reasonable. But in my case, I'm very surprised and very honored. By the way, in textbook, Plasma Astrophysics, I and Tajima-san noted this kind of observation. That is, this is a hard X-ray light curve. And the microwave light curve also shows very time variable light curve. And this is almost fractal-like. And we thought this kind of light curve may be evidence of a fractal distribution of a plasmoid. And if this is true, we can connect the microscopic scale to macroscopic scale through such a fractal connection. Similar idea has been proposed by many researchers in a different field. And one of my graduate students, Tanuma-san, has developed a nice MHD simulation and found that multiple plasmoids are generated in the rate evolution of a current sheet and produce such a very intermittent energy release with plasmoid ejection and become smaller and smaller like this. So this become fractal. This is because MHD with a large magnetic Reynolds number is almost independent of scale, so scale-free physics. Therefore, this can occur. And recent plasma physics, many plasma physicists is approaching to this possibility. And also from solar observation, we are in the best position to confirm this idea because we can image solar flare current sheet. And one of my graduate students, Takasawa-san, discovered multiple plasmoid in a flare current sheet like this. In the future, higher spatial resolution observation would reveal more and more smaller plasmoid. And by the way, previously, Parker probe discovered a very large-scale plasmoid in the interplanetary space. I'm very impressed, happy to hear the talk. And plasmoid is very useful to accelerate particles because if plasmoid interact with shock, this is a standard model of flares, very high-speed jet with a lot of plasmoid with different sizes. Finally, collide with termination shock, first shock. Then we have first-order Fermi type acceleration. And even if spectrum is not a power law for a single collision, if plasmoid distribution is a power law, then final particle distribution become power law. This is a very rough, simple idea, but published in physical review letter. So therefore, this is not well known in solar physics community. So please remember this idea. And finally, I will talk about superflares. And these are developed by Maehara-san and especially young, at first undergraduate students, not. This is a statistics occurrence frequency solar flares, microflare, nanoflare, famous diagram, frequency at vertical axis and flare energy, horizontal axis, and power law distribution. Whether the superflare larger than the largest solar flare occur or not is a very important question. And if such a statistics rule continues more than 10 to the 33 erg, that we call superflare. Superflare may have affected life in the past on the Earth. The cause of mass extinction of life, such as dinosaurs, might be due to superflares. At first, I started to discuss this as a kind of joke, but my friend, archaeobiologist, asked me, please study seriously. Then I started to think about from astronomical point of view, and I found X-ray astronomy already observed a very big superflare, 1 million times more energetic than the largest solar flare. So even our sun produced such a super flare when the sun was born. And a very scary question. Can superflare occur on the present sun? And we know that sun is not young, already 4.6 billion years old, and slowly rotating. This is important. So that it has been believed that sun would not produce superflares. Please feel free, relieved. However, amazing discovery was made in 2012 by Maehara et al. And if you remember the statistics rule, if we prove the superflare larger than 1,000 times than the largest solar flare, time scale becomes 10,000 years. So we need 10,000 years to prove this. But our observation, modern observation using telescope, is only 400 years. So how can we observe the sun for 10,000 years? And I belong to astronomical observatory, so I thought, if we observe 10,000 solar-type stars similar to our sun for 1 year, then we can get the data similar to the data obtained from 10,000 years of observation of the sun. And I asked many astronomers whether there are such data or not. And Sekiguchi-san of NLJ kindly told me, Kepler satellites taking such data. This is, of course, you know that exoplanet hunting space telescope. And 0.95 meter diameter, observing 160,000 stars near the Milky Way. Among them, roughly half are the solar-type stars. The data taken 30-minute time cadence and open through internet. So I started to analyze the data, wanted to analyze, but so many data. And the problem is my young colleagues, postdoc researchers, didn't believe in the possibility of a solar superflare because the sun is old, slowly rotating. But I really wanted to analyze the data, but no one collaborated with me. So I asked the first year undergraduate students, Kyoto University, because students have a lot of free time. I was teaching introduction to electromagnetism, and then asked students. Then 5 students came to me, and fortunately, they are not familiar with astronomy. Therefore, I told them, if you find a superflare, that's a great research, and they thought seriously and start to search. Then, surprisingly, they found 365 superflares on 148 solar-type stars. And finally, the paper was published in Nature, including those undergraduate students. Please remember, they started the research on first year. This is the third year. First author became Dr. Maehara, postdoc. But he told me recently, he wanted to reject this possibility and carefully analyze. But finally, he couldn't reject. So. And this is the typical example of light curve of superflare stars. This spike is a superflare. 1.5% brighter than the average stellar brightness. And total energy is 10 to the 35 erg. And the interesting result is that stellar brightness itself shows some variation, time variation. This is the other example. Even larger superflare occurs, 8% of a stellar brightness. Total energy nearly 10,000 times than the largest solar flare. And all solar type stars showing superflare show such brightness variation of star itself. So what is the cause of the stellar brightness variation? Probably this is likely due to rotation of a star with a big star spot. This is one of the biggest sunspots in the recent years. But our solar type star observation suggests this big spot and big white light flares. And if we plot the superflare frequency here, then, and this figure is renewed, and recently Dr. Notsu made a very careful analysis and found that superflares are 1,000 times more energetic than the largest solar flare occurs once in 5,000 years. In the case of a 100 times superflare, occur once in 500 years. So these are not a very distant future, can occur in 10 years or so. And amazingly, in the cosmic ray community, they found evidence of a strong cosmic ray 1,000 years ago in Trilling in Japan. And now this is considered to be evidence of superflare with 10 to the 34 erg. Also, students of Department of Literature, he can read all the literature and found this kind of evidence of bright aurora observed near Nagoya in this case. So usually such aurora cannot be seen in the central Japan, but once in 100 years, this kind of very big aurora occurs. That may be evidence of a superflare. If superflare with energy 1,000 times occur, what would happen on our Earth and civilization? All artificial satellites would be damaged. All astronauts and some of the airline passengers would be exposed to fatal radiation. Ozone layer depletion would occur. Radio communication trouble would occur all over the world. And global blackout would occur all over the Earth, and aurora can be seen everywhere. And the worst result may be all nuclear power stations would be lose electricity, and hence in a state of meltdown, like a Fukushima disaster. Okay, so maybe better to stop, but briefly. In order to observe stellar flares more, we, Kyoto University, succeeded to develop a new 3.8-meter Seimei telescope 2 years ago. And last year, we started to observe transient objects, such as supernova, gamma ray bursts, and stellar flares, super flares. And this is the first segmented mirror telescope in Japan. And all our technology have been developed by researchers. So cheapest telescope in the world. And the lightest telescope, so very good for transient object observations. And in the last October, I succeeded to observe stellar flares for the first time in my life with the same telescope. This is the light curve of a stellar flare, M dwarf star EV Rack. And Dr. Maehara helped me very much. This is very convenient observational system. I didn't have to do anything. I only take a picture of this display. Okay, summarizing my talk, the universe is full of explosion, flares and jets, and high energy particles from them. The reason why the universe is full of explosion is that magnetized plasma are so unstable and active. Extreme activity, such as super flares on the sun, may have been related to the origin and evolution of life on the Earth, whereas it would be extremely dangerous for our civilization in near future. So our science is related to broad fields. Okay, thank you for your extent.
So we all had a masterly exposition from a master, even though it is a little bit late, but still we can take a few questions. So are there any questions and comments? Yes.
You see a large number of flares with scales in terms of this energy in stars like the sun up to what you've discovered in other stars. Now, if you think of their origin in magnetic fields, would you think that the scaling would actually be directly related to the size of the active regions which spawn these flares, or could this also be related to a different mechanism which can extract more energy out of less flux?
Yes, size of active region, we use the size of spot, is important. It's easy to understand. For big spot, we can store a lot of energy, more and more energy. And maximum flare energy is the case that the star is covered by spot, all surface is a spot. And very young stars like that.
So in that connection, I can mention that in the collaboration in which I was involved with Professor Shibata, we also realized that for the sun to produce super flares, there has to be sunspots of very large size. And my contribution in that paper work was to figure out whether this is consistent with our current understanding of solar dynamo or not. So any other questions? Yeah, there is.
So you mentioned about the 5,000 years. So it's much shorter than the previous one, 10,000 years. So the value, 5,000 years consider the direction of the flare. I mean, when you think about the, say, flare has an angle. So if you consider that Earth will affect it
Ah,
not
yes.
with that
Yeah, you are
period.
right. So actual probability to have a big magnetic storm is once in 20,000 years or so. Probability of colliding CME to the Earth is probably 1/4 or so, because CME is very wide. But even X-ray is very dangerous.
Oh, yes, that's right. Thank you.
So Chia Sen had a question just behind you.
Actually, I'm curious about the smallest scale of flares. So you have a table showing this, the small scale to the large scale.
Mhm.
So I wonder if there is a minimum size of the flares. What would be the minimum size, and what would determine? Or
Yes.
you can go as small as you want.
Yeah, that is a good, interesting question. And usually, if we are interested in the flare with the non-thermal particles, then the flare size is determined by the thickness of the chromosphere. If magnetic group is embedded below the transition region, then density is high. So it's difficult to accelerate particles. Only loops appearing in the low density corona, reconnection can accelerate particles. But the reconnection itself can occur even in a dense photosphere. But in that case, non-thermal particles cannot be generated. But some brightening or jet may be produced. And one of my graduate students is now developing such a photospheric flare, nano flare, and jets, and which would be confirmed by DKIST in recent years.
So Rajmal, yes.
Yeah. You showed that plasmoid is essential for fast, reconnection rate. And in your model also, in unified model. But for without plasmoid, faster reconnection is not possible, or what kind of parameter governs for faster reconnection if the plasmoid is there?
Faster reconnection. I think if plasmoid ejection can occur, then fast reconnection become possible.
Okay.
That is also can occur in a chromosphere, dense, low temperature chromosphere. That is very important. Usually, laboratory plasma physicists and magnetospheric physicists consider only low density, high temperature plasma.
No, but in your
causing
unified
fast
model,
reconnection.
you have shown that even for microflares to the macroflares, everywhere plasmoid is essential. So,
And so returning to the question by Lin-san, if we include such a low energy flare-like event, smallest flare-like event may be a intergranular ray size.
Okay, so you have one question here, and then after there, so yeah, you can ask.
So, could you explain how the occurrence of superflares depend on the age of the star?
Excuse me.
Sorry, can you
Could
speak?
you explain how the occurrence of superflare depends on the age of the star?
Occurrence of superflares, how it depends on the age of the star.
Yeah, that is also important question. When the stars are young, very active, many superflares occur. But as the star become older, rotational speed becomes slower and slower, then the sunspot size becomes smaller and smaller. Therefore, flare energy becomes smaller, smaller, and frequency becomes smaller and smaller.
So there's one question over there.
In the black hole accretion disk simulation, you always initialize a vertical coherent magnetic field. What can be the possible source for this magnetic field? I mean, what do you think?
Yeah, that is also important question. Now, in our case, we simply assume the vertical magnetic field. And in the case of a star-forming region, there is already global magnetic field in molecular cloud. But in a closed binary systems, there are no such global field. So in that case, probably dynamo become important. Dynamo generate magnetic field in the accretion disk. And the dynamo generated field can interact with the rotation of a disk, and finally gets formed. And we confirmed such a case by numerical simulations.
But we would normally expect the field lines to open up like this. So did you also do a self-consistent study why field lines, instead of opening up, remains almost vertical and parallel?
Because twisted magnetic field can pinch.
So, pinch.
So to form a straight jet-like straight structure.
Okay. So any other question? Okay, so yeah, Professor Deshpande, yeah. And then one more question there, and then we shall close.
In the process of twisting a bundle of magnetic field lines, does one encounter situations of wreath formation, like when we twist?
What formation?
Wreath formation.
Wreath formation.
Like when we twist a towel,
Right.
Right.
So there are some topological theorems of twist and ride. There are some
in the case of a jet.
Yeah, something like that. Yeah, in the case of a ride.
That is also interesting future direction. In the case of non-solar astronomy, still observation of magnetic field is very low level. And sometimes astronomers hate magnetic field because it's a bit difficult. But in future, yeah, this kind of discussion is important.
So I think we can take one last question or one.
Yeah, I have just a general question. I'm curious, after we find so many so powerful super flares, and I mean do we consider this as a criteria for when we look at habitable planets or expect any signs of life forms? So do we look at the stars and their activity? Because NASA is hunts for those habitable planets, and then they keep searching for them. So
yeah, that is also important direction of this kind of research. So I wrote extreme activity on the sun, not only on the sun, but on other stars, may have been related to the origin and the evolution of life through habitability. So some days ago we discussed Sun-Earth relation can be applied to star-exoplanet relation, and eventually related to life.
Okay, so on this note, let us thank Shibata-san again.
Thank you very much.